Okay, we then going to introduce multi-flow versus single flow, which is an open. Why it's going? Okay, which is how the controller is going to work. Will it use a single flow or will it use a multi-table to describe the flows? And last, I will introduce the what we call tag is a new way for context offload. So first, about RTE flow. RTE flow is the API for offloading for DPDK. It is consisted of matching and actions. Currently the match has to be some type of header of the packet. For example, here you can see you have the MAC, the Ethernet layer, you have the MAC address, you can match the source MAC, the destination MAC, the type, and so on. The next layer will be the IP, it could be IPv4 or IPv6. You can match on the IP fields. Usually it will be source IP and destination IP, but other fields can be matched as well. And next layer will be the transport. It will be UDP or TCP. Again, you can match on the header. You can match on the source port and destination port. You can match on the TCP flags, and so on. You can do more than one match. You can have more than one layer. If you use tunneling, you can do match on the outer layer and then match on the tunnel itself. It could be VXLAN or Geneva or whatever, and then you can match on the inner layer. You can do partial match. You have a mask. So for example, if you want to match only the source IP, only the prefix of the source IP, you can do that with mask. Most of the fields are supporting. And you have also priority. If you can have overlapping rules with priority, first we're going to try to match over the highest priority, and then we go to the lower priority. The actions, okay, so this is a list of match. Once we have a match, we have to do actions. The actions can be actions that can, for example, count. They can modify the packet. For example, do NAT, SNAT, rewrite the packet, rewrite the MAC address, decap, and so on. And the last action must be what we call a fate. We have to know, the hardware have to know what to do with the packet. So it can be output, it could be drop, it could be go to software, to the controller that will tell what to do with the packet, and it can be jump to the next table, which I'll explain. Okay. This is example from OVS. I'm taking the example from OVS. In the OVS code, currently there's no full hardware offload. What we have in OVS community in DPDK is only what we call classification. OVS is a multi-flow controller, multi-table flow controller that I will explain later. And what we do in offload is only matching the first flow and classify it. We save the OVS, the parsing of the packet, and we give it a mark. The mark identifies which flow in the software this packet belongs to. So for the first table, on the first match, we save the classification. You can see how the code looks like. There is a match, in this case, on the target port and the source port and the target port. And there is a mask. It can be 0. It could be, in this case, we support only 0 or full. The next is an action. So this is also from the OVS. So in OVS, we only have marks. So this is how it looks like. You add the mark ID. You add it to an array of actions, and you configure it to the hardware. Once you configure a rule to the hardware, let's say we have a single table for this case. When the packet arrives to the hardware, we first try to match according to the rules that were configured by the user, by the RTE flow API. Once we have a match, we execute the actions. If we don't have a match, there's a default rule that the user can change, but the default rule means that we are going to the software. Okay? In the actions, we can steer the packet. I'm not going to talk about it in details, but you can steer the packet to any VAF. If you're working in switch mode and you have the uplink. You can switch the packet to any of the VAF and the virtual functions. Also, if you have two virtual functions, you can configure the hardware to send the packet, doing in-cap, decap, NAT, whatever, and give it to the target VAF. All this you can do in hardware. The software will not see the packet. Okay, so multi-table. So the controller that configures the data plane, there can be a single flow and a multi-flow. In a multi-flow, we have several tables, one after another. In each table, we have match actions with priority, like I described, and actions. But the only difference is that you can have an action jump to the next table. Okay, you're doing what you do on the first table. The action can be, for example, change the MAC address, and then jump to table number 7. Here is an example for OVS. This is how OVS is working in software. In this case, you see a data plane flow. And when the actions is going to connection tracking, and then go to recircle ID number 9. Recircle ID is a logical table. Only flows that will be inserted on recircle 9 will be inspected in this case. So it's like a table. What we expect in table 9 is that the next flows will try to match again against the state, if this connection was established or not, if the packet is valid, and so on. Why using multi-table? First, flexibility. In many cases, you need to match different criteria and do a different action. For example, you have to do NAT, so you have to match on the IP and change it, and you have to do quality of service. So you want to match, for example, the TOS marking. So if you want to do both in a single flow, you have to supply a matrix. You have to configure a matrix of all the options for this flow. A second reason is multi-stage processing is in many times it's much more easier to do in software. For example, if you have forwarding and connection tracking. The target of the connection tracking is usually security groups. You want to do a security policy. And the rest of forwarding rules is the next hop. You want to configure the next hop. If you are running on cloud infra, for example, you have to in-cap with the underlay network and set it to the next hop. So if you have a single flow for each flow and now the forwarding has changed for some reason. For example, if you have ECMP and one of the next hops is not working and you have to change, if you have a single flow, you now have to update all the flows. You have to find all the flows that are directing to this next hop, remove them, and add again with a fix. If you have a multi-flow, you have to change only one flow. So rules can be more generic. I'm not saying that multi-table is better than a single table. This is use case dependent. There's a lot of big companies. One of them is Microsoft. You can read. They have papers about their switching, and they are using a single table. Okay, so this is how multiprocessing can look like. We have few stages of processing. The first one will be classifier. We match, for example, the 5 tuple, and we set a classification ID to the flow. The next will be forwarding. For example, it will be the underlay. You have to in-cap with VXLAN or whatever and set the MAC address. And the last one will be quality of service. You want to give a different rate for each application. So currently, in hardware offload, we cannot do that because there is no way to pass the information from table 1 to table number 3. Okay, there's a lot of workarounds people do, like in-cap of another packet, or put it in the TCP options, or a lot of workarounds. But this is not. I'm suggesting you won't do that because you're going to change that later. This is how it looks like in the tables. Okay, you have hardware table. Table number 0, you have a match, and then you have an action. The action will set the classification, which is not part of the packet. Okay, we are not modifying the packet. And on the next table, you want to match this number that you set on table number 0. Okay, so as I said, there are some switches that are multi-table and some are single table. In the case that you want to hardware offload a multi-table switch, you now have a problem because we have a context and we have no way of moving it. So what we can do is compile the flows together. Okay, we are tracking a packet. The packet will go through the switch. We collect every flow, every software flow that the packet went through, and then we create one flow that combines all the matches and all the actions. But this solution, it can be done, but it has a lot of drawbacks. It's not following the control. For example, in OVS, it looks very different. It requires a complex logic of knowing when to add and remove flows, because if you remove one of the flows, you have now to keep all the flows that were generated as part of this flow. Counting, if you're doing decap on the way, you get different numbers on the way. You have to adjust the counters, which is hard. Also, combining two flows, it's not always easy. For example, in this example, if A1 is changing the IP and M2 is checking that IP, you have to adjust that in the flow. So it's not just putting all the matches and all the actions. You must have a logic. In most cases, it requires exact match, which means in some cases you will have much more flows in hardware than you would have with a multi-table. Of course, it's a trade-off. Okay, the right approach is depend on what you want to do. Usually, if you want to be generic, you will do a multi-table. If you are only solving a local problem and you own the entire system, you might choose a single table. There is memory. There is packets per second. If you have multi-table, usually you have more latency on the packet because you're doing more. You're jumping to tables. You're doing more matches and more actions. And also, I talked about it, the update rule, for example. If you have a single table and the forwarding change, you now have to update 1 million rules, which is a lot. Okay, RTE flow tag. So in DPDK 1911, there's a new API which is called RTE flow tag. Okay, this is a generic API for setting some information, some scratchpad that will follow the packet. Okay, it's a 32-bit data. It's like more like an array. You have a few such tags that you can use. You can use with bit granularity. Since this is a hardware, you can think about it as an MBUF header. Okay, we don't want to add too much data in it because we will lose performance. We have it, but we want to use it carefully. So you can set with bit granularity, and you can also match with bit granularity. So if we go back to the classifier, so we can do it now with the tag. Okay, on the classifier, we set the classification. This is a hardware action. Okay, when you have a match, you're doing set on the tag, and the packet will continue to the next table. And then the quality of service table, we can check. We can match this this tag. If it's video, we go to quality of service that is doing video. Okay, so tag is limited. Okay, it's not like a memory. Now you have a scratchpad 1 mega. It's limited in length. It has performance impact, so you want to use it carefully. And sometimes you have to adjust the software logic to use it. Example from the OVS. In OVS, when you have a decap action, what we call tunnel pop, and what they call, when the action is done, when the OVS is decapping the packet, it takes the outer IP and the tag and the VNI, for example, in VXLAN, and save it in the packet metadata. There is a DP packet struct that inside this struct the metadata struct, and inside this struct, this is the outer tunnel metadata. And later, the OVS can compare this metadata to match in the following flows. If we use a tag, we don't want to save, if we talk about IPv4, we don't want to save the source IP in one tag, the destination IP in one tag, the VNI in one tag, 3 tags just for this. If it's IPv6, it will be 9. So what we are going to do, we're going to do a mapping. If you think about it, how many nodes do you have in a cluster? 10,000, 20,000? How many are going to connect between them on the same time? 1 million, 2 million? And this is much higher than in real life. So we are doing a mapping. Instead of putting this information, we create in the software, before we do the hardware offload, we map between IP, source, destination, and VNI to a tag ID, and we use this tag ID instead of matching the 3 tuple. Okay, in this way, we saved a lot of our tags and also saved performance. Now we go to the connection tracking or the OVS. Okay, this is the example of the OVS. One of the problems we had in offloading OVS connection tracking is this context, that we didn't have a context. For example, in connection tracking, you have zone. The user can match zone. Zone is not part of the packet. You cannot put it in the packet. Another thing is are called city mark and city label. Those are 2 numbers that are set by the user. This is metadata. This is not part of the packet. And if you want to do hardware offload, you must compare them as well. Another thing that in connection tracking that is being compared is, of course, is the connection state. There is established and reply, and if it's a new connection. And so this is called the city state, which is also not part of the packet. This is part of the connection tracking state. In the OVS, when the packet goes to the connection tracking and there is a match, the software will put this information in the packet metadata. When the packet continues to be processed in the OVS, those values can be compared on the next rules. Okay, and this we couldn't do in hardware. Okay, so how we use the tag to compare it? Okay, if we now want to offload a connection tracking flow to the hardware, we have a match on the 5 tuple. We also have a zone. Zone can be implemented as a different table, or it could be a metadata. It's less important. But then we have the actions. The actions of the connection tracking, we have now to save this metadata into the tags we have. This is our context that we're going to use later. So we have to encode those bits into tags. Some are very simple. For example, zone is 16 bits, so you just use 16 bits of one of the tags. Here I have a mistake. The second one is not a zone, it's a city state. City state is 8 bits, so it's not a problem. You can use both on the same tags. The 2 other fields are mark and label. Mark on OVS is 32 bits, which is not a problem, but label is 128 bits. This is a very long number. We'll have to use 4 tags for it, which will waste our resources, also waste performance, because now you have to compare 4 tags instead of 1. So the suggestion here is to do a reduction. This depends on the use case. One option for reduction is to do a mapping, keep a map of label to a lower number, for example, 32-bit. But unfortunately, label also have a mask. If you're doing a mapping, you cannot do mask later. So this is a problem. So what we saw with customers is that label is not used with high numbers. Usually they use only the lower 32 bits. In many cases, it's only few values, 10 values and nothing more. So what we suggest here is trimming, cutting the number in 32 bits and using only that. Of course, that if you have a flow that is using something that you cannot support, we will generate an error and will not offload it. We will never offload something that is not correct. So the common use case can be supported. We now can offload connection tracking. This I will leave for the OVS conference to show the numbers, but I can say that they are amazing improvement. And this was a real blocker for us to do this offload. And it is introduced in 1911, and once OVS community will integrate that, we can push our code to the community. Okay, so again, this is the same issue, the same offloading. You can see first we have the match. On the match, of course, the match is per port. This is explained at the beginning. The flow, the table is per port, so you don't need to match the ports. If you configure it on port 5, it will always be 5. And then the actions, you're now adding new actions, set tag city state, we set the state, set tag zone, we set the zone, and then you jump to the next hardware table. And on the next table, you can match those values. You have a match, you use the same tag index and the same mask, and you can do the actions. Okay, so to summarize, so the tag is a generic API. It's not OVS API. It doesn't say OVS. It's only a scratchpad for keeping information. It can be used, for example, we have cases in 5G, UPF, when you want to do, there's a quality of service flow indicator that you want to keep and then use it, for example. For OVS, we use it for connection tracking. It allows multi-stage processing. Talked about it a lot. You don't have to do a single flow, but in case you want to do a multi-flow, in many cases you will have to save some information, and the tag will allow you to do that. And it's not will be supported. It was already pushed to the upstream and can be used in DPDK 1911. Okay, 5 minutes for questions. I'm waiting for the...
Oh, thank you. I have a question about at the first part, you mentioned the multiple stage lookup and then talk about the tab for connection tracking. So is there any relationship with those parts when you deploy these offload features, or they are totally independent?
Can you speak louder? I can't hear.
Okay. My question is, you talked about the multiple stage lookup and also talked about the tag action for the connection tracking offload. So my question is there any dependency, or the two features are totally independent?
Dependency on what?
These two features.
No.
No, totally different.
This is a feature of DPDK.
Yeah.
That we used in connection tracking. This was a blocker for connection tracking offload, but it can be used, it's a generic feature, it can be used anywhere.
Okay, thank you.
Thank you. Very interesting. You spoke about multiple tables, but you mentioned in the naming how you treat this in OVS. I think I missed how you add this in RT flow. Is there a table ID in RT
There's a
flow?
jump, yeah.
Jump to RT, and then there's a table ID?
Yeah, there's table ID in the struct when you configure the egress, transfer, and so on, there's table ID. And for the action to jump, for that, there's a specific action for jump.
Okay, thanks.
No.
More question. Oops. Do you have an idea for what the cost is of adding flows, removing flows?
I can't hear.
You can. Oh, sorry. Is this better?
Yeah.
Do you have an idea of what the cost is for adding flows or removing flows? Do you have any benchmarks?
How much it costs to move?
Latency. I imagine, right? For OVS, you might want to manage.
Hardware dependent. So I can say about how our hardware we can support 300,000 flows per second update rate.
You said 100,000 flows per second, right?
300,000.
Okay, thank you.
One call. Hi, I like this a lot. It's good to see the unification of the flows. And one question I had was, there seems to be a lot more actions in OVS than there is in RT flow, or is there some of the action types that you just can't do, and what do you do when you see those?
We are adding actions. For example, one that we are going to add is DP hash. But most of the action we do support. Can you specify?
I was thinking like, the one I was thinking of was mirroring, which is...
Mirror, okay.
Which isn't there in RT.
Yeah, for DPDK, yeah, okay. We need to add it. We don't know how. The hardware can support mirroring, no problem. So we have to think about a good API, how to configure it and be consistent. The way also that OVS is doing it is a little bit out of it. You configure the OVS and not with the OpenFlow. It's a little bit inconsistent, let's say.
Great.
Yeah.
Thanks. Oh, yeah, we get one more.
Yeah, sorry, one more question is about, you mentioned that there are multiple stages, multiple tables, and multiple actions. So how do you test them? Since there will be many combinations, how do you ensure each pass or each flow or this function correctly?
How I pack them?
How did you test them to ensure this function works, since there are many combinations and multiple stages, multiple tables, and multiple actions? There will be, I think the combination for the all the test scenarios will be maybe hundreds or thousands. So how do you manage to do that, or not too much testing? Or?
You have a building block of matches. This is why a match, this is, I showed in the beginning, you have a match only on the internet, only match on the IP, only match on the UDP, and you combine, you build your own match that you want, okay? And then you give in the RT flow, you give an array of matches according to what you want. And also in the actions, you have many types of action. Each one is a building block. You have count, you have decap, you have output, and so on. And again, you build your own list of actions, and you give it to the hardware. Now, if it's a combination that the hardware cannot support, you will get a failure. But usually, we are not combination dependent.
Okay, the question is for how to test them. This is
how to test?
How the company, how Mellanox tests these functions. Since you mentioned about the logic from the development side that this function is designed with different blocks, but how to ensure this working as designed or expected? Is there any tools or something to demo?
You have a test PMD. Okay.
Okay, basically what we're doing is, since there is a limitless options, close to limitless, every day we have different regression, different testing. We know what the expected results should be according to the random actions and random matching that we selected. And we're comparing them and checking to see. This is the main idea. Does it answer the question? It's not full, but since it's every day, it's random, it's generated again and again. So our coverage is pretty close to 95% even. Again, from the actions, maybe we're not testing all IPs, but we're matching on IPs. So it's quite covered. I assume more than 90%. Thank you.
Great, thank you. Thanks.